Okay, hopefully you've already watched the video about the atomic spectroscopy demonstration. Uh, what this video is about is helping you do the lab. So here we're looking at the document that says atomic spectroscopy of hydrogen. And you can see there's the objectives and there's an introduction. And what we're going to do here is we're going to go over the introduction very briefly. So here you can see we've got this very important equation, which is basically C is equal to lambda nu. This is written a little bit differently where it focuses on frequency, which is that nu. So that thing that looks kind of like a V is actually frequency. Okay, so that's a pretty important equation. And I'm writing it down on a piece of paper here, which we're going to be looking at in just a moment. And the other important equation is that E is equal to H nu. So often these two are combined together to give you E is equal to HC over lambda. Now, what is C? C is the speed of light, and that's something you should probably commit to memory. And the thing that looks like an upside down Y, so to speak, is the letter lambda, which stands for wavelength. The thing that looks like a kind of a cross between a V and a U is the letter nu, and it stands for frequency. And the units for frequency are 1/seconds. Some people say cycles per second. And the units for the speed of light are meters per second, and the units for wavelength are meters. Usually in this case, we like to use nanometers, and we'll find out why shortly. You can see that there's a figure here that shows a glass tube with a high voltage power supply attached to it. And if you watched the video demonstration and you saw that little neon light, that's what we had there, only the tube was vertical instead of horizontal. The high power supply, high voltage power supply is pretty dangerous. And so that carousel that I had is pretty handy. Okay, so here you can see that we have the Planck's constant, and that's something that you kind of want to commit to memory. On the quiz, I will make that available to you because I don't want you to stress too much about it. But on your next exam, that's something you probably want to write on your note card. So this is called Planck's constant. Some people call it a proportionality constant because, well, all constants are proportionality constants. Okay, so H is Planck's constant. So we're not going to read through this directly. Now, a really interesting thing in this particular one is something called Rydberg's equation. And Rydberg's equation is given there where you have 1/lambda is equal to R 1/m² minus 1/n². Now, for our particular purposes, we don't need to memorize this. But it is important in that this equation was developed so that you could actually calculate the visible wavelengths of the hydrogen line spectrum. And it worked really well. And it actually worked well for predicting ultraviolet lines and infrared lines, which we can't see with the visible eye. So Rydberg's constant is something that you definitely do not need to commit to memory for the test, or for the quiz, I should say, but it is something that you might want to write down for your note card. Now, it's interesting, it says m to the minus 1, which is the same thing as saying over m, okay? Now, another interesting equation we have here is r sub n. So r sub n is the radius of the first orbital. So here we're talking about an atom where the proton is in the center and an electron orbits around the atom in a circle, okay? Kind of like the planets orbit the sun. And kind of like the planets orbit the sun, the planets kind of stuck where they are in orbit for all practical purposes. We don't worry about the planets spiraling into the sun, nor do we really worry about the planets spiraling away from the sun. And that's the same thing we would think about an electron on a hydrogen atom, is that the electron could be anywhere around the sun, but it has to be at particular places. It can't be in between. For instance, the electron could be where Mercury is orbiting the sun, or the could be an n equal 1, the first level, relative to the proton being the sun. Or it could be at n equal 2, which would be Venus, n equal 3, which would be Earth, n equal 4, which would be Mars, and so forth and so on. So just like the planets, the electrons can be a particular distance from the nucleus, but nowhere in between. So that's kind of interesting. All right. So this next equation where you have R sub n, the reason they write this equation this way is because everything in the bracket is a constant. That is to say, it doesn't change. So H is a constant. Pi is a constant. M sub v is the mass of an electron. That's a constant. E squared is the charge on an electron. That's constant. So you have all of these things that are constants times n squared, and that gives you the radius of each level. Now, each level is named level 1, level 2, level 3, level 4. Sometimes we call it shell 1, shell 2, shell 3, shell 4. Or orbit 1, orbit 2, orbit 3, orbit 4. There's lots of different things you could call these things. Orbit, shell, level. Okay, so you can see that if we look at this, we can change the formula to R sub n is equal to 5.29. And for this lab, we're not too concerned about having a whole bunch of significant figures. So we're just going to go for 3. And we're going to have 5.29 times 10 to the minus 11 m. M is meters, n squared. So the unit is built into this equation where you're actually going to be calculating the radius in meters. And you just plug in the different n's. So this n is called the principal quantum number. And again, they would be the first orbit, second orbit, third orbit, or first level, second level, third level, or first shell, second shell, third shell. Now, you can see with this next particular cartoon, I should say, what we're looking at is a light source going through a prism. And you can see with the very top image that the light source goes through the prism and you get Roy G. Biv, a continuous spectrum of light. It looks like a rainbow. Red, R stands for red, O for orange, and so forth. Now, the image in the middle shows a gas discharge tube. So this is normally a gas that you put in there. Often you put an element in there. So we're looking at the signature of the element. So when you put voltage through it, it lights up like a light bulb. You send it through the prism, and what you get are distinct lines. You don't get a continuous rainbow of color. You just get distinct lines. And it's kind of interesting here because the image that you see in the middle there is actually not seen. You see the image on the bottom. That is to say, you see a black screen except for those places where light is being emitted from the gas discharge tube and going through the prism. So basically, you see a black screen with color on it. And for a hydrogen spectrum, you'd see basically four lines. 2 would be really faint, 2 you'd be able to see, but you would see 4 lines in the visible region of electromagnetic radiation. Now, this bottom image shows you if you put a light source through that same gas discharge tube, but this time you don't light up the tube. You're just putting light through the gas discharge tube. So what happens here is the rainbow of light goes through into the gas discharge tube. But what comes out is pretty amazing. You get a rainbow of light coming out. So do you see the black screen? That's supposed to be the rainbow of light, just like above it's a black screen. So what are those little bars there? Those bars are places where no light comes through. So actually what this would look like, it would look like a rainbow of color with 3 black lines in it. Because what does light look like when there's no light? It's a black line. So here on the top, you have what's called a emission spectrum because the light source is emitting light and going through the prism. In the middle, you have an emission spectrum because the gas discharge tube is emitting light and giving you a line emission spectrum. The bottom one is called a line absorption spectrum because what it does, those 3 lines which are black and there's no light there, they are wavelengths of light that are absorbed. And it turns out that those wavelengths of light are exactly the same wavelengths that are emitted in the second figure. Okay, so out of all of that, the important equation that we want is this E sub n, the energy of an electron in the nth level. And you can see that it's equal to a whole bunch of stuff uh, that's in brackets, which is a constant times 1 over n squared. And so we want this minus 2.18 times 10 to the minus 18 joules over n squared. That's the thing we want about the that one. Okay. Now I'm going to scroll down, and you can see that we have here another very important equation. And here, I don't really like the way they arrive at this equation. We're going to skip this, and I'm going to show you how I arrive at this equation later. So now we get to the experimental procedure here, and you can see that this says caution, wear eye protection. So if you saw me using that ultraviolet or saw me using the carousel earlier today, my glasses offered all of the protection I need for my eyes because they absorb ultraviolet light. Okay, so here you don't need to wear eye protection because we're not doing the lab person to person. You just kind of watched it online. Okay, so here it tells you, first of all, to calibrate the wavelength scale. That's optional, and I did not do that. That's not important for us. And then we're supposed to look at the emission spectrum of hydrogen, and we did look at that, and but we don't really need to write down those numbers. That's not very important. Part 3 says the Bohr's model of the hydrogen atom. So we have 4 parts here. 1, calculate the radii and energies of the first 10 allowed orbits of the hydrogen atom and record the results. So this is actually part of your lab, but we're going to amend that. So when we have part 3, we're going to say the following for number 1, calculate the first 7. Okay. Calculate the first 7 radii. And then number 2, use the results from step 1 to calculate the change or the energy. Let's see. Oh, I should say part 1 has 2 parts. Calculate the first 7 radii and calculate the first 7 energies. And then number 2 is going to be calculate the change in energy that they give you. They're going to describe particular changes of energy. And from that change in energy, you're supposed to actually get the wavelength. So there's 2 parts to part 2 here. I should say part 3, number 2. And then you can see for part 3, number 3, it says on a wavelength scale, construct an emission line. We're going to do that. So I'm going to write construct emission line. And I'm writing these notes on a piece of paper, which we'll be looking at in a little bit when I switch my share screen. And then number 4 is going to be construct an energy level diagram. And then number 5, which isn't listed there, is going to be construct a radius diagram. So that's what we're going to be doing for this lab. 1, calculating the 7 radii for the first 7 levels or first 7 orbits. We're going to calculate the energy of each of those 7 orbits. We're going to calculate the change in energy when you go from one orbit to another for specially designated transitions. Those are called transitions when you go from one orbit to another. And then we're going to calculate the wavelength that is associated with each of those transitions. And then we're going to draw an emission line drawing, and then we're going to draw an energy level diagram, and then we're going to draw a radius diagram. Okay, so those are going to be the things, the calculations that we're going to be doing. And we're going to get to the assignment a little bit later, but let me go ahead and show you what we're going to be doing here. So we're looking at right here, if you can see here, we have a table that says calibration of the wavelength, optional part 1. We didn't do that. So I don't expect to see that in your lab notebook. Part 2, the emission spectrum of hydrogen. Again, we did not do that, so I don't expect to see that in your lab notebook. Part 3, Bohr's model of the hydrogen atom. So you can see here that we have a table that says quantum number, and quantum number is another way of saying orbit. Notice that we have a table here that goes all the way to 10. We're only going to go all the way to 7. Okay, so we're not going to go to 10. We're only going to go to 7. And we're going to calculate the radius, and we're going to calculate the energy. Now, I want you to notice that the radius says times 10 to the minus 2 nanometers. So we want all of our answers to be times 10 to the minus 2 nanometers. And the energy is all times 10 to the minus 18 joules. So we want all of our answers to be times 10 to the minus 18 joules. And what I'm going to do is I'm going to show you how you can do that fairly easily based on the formulas that we were given at the beginning of the writing. Now, if we look at this next section here that says label M to N and the wave energy and the wavelength, these are the calculations for the transitions that we want to do. Now, we're not going to do all of these transitions. So here, let me tell you which ones we want to do. You definitely want to do A. And the reason you want to do A is because you can check your answer and see if you're right. Now, they have 5 significant figures. We're going to end up with 3 significant figures, and hopefully it comes out to be the same answer. The same with the wavelength. We'll come up with 3 significant figures. And, if we get 94 or 95.0, we'll call it a day and say that's good. So we're going to do letter A. We're going to do letter E, F, G, H, and then we'll also do letter I. So we're going to do A, E, F, G, H, I. And I have that written down. We're going to calculate the wave energy, and the wave energy is simply the change in energy. And we're going to calculate the wavelength for each of those transitions. Now, for the emission line spectrum, what we're going to do here is we'll put the wavelengths that we see that we calculate in the above table down below. So I don't know if you can see that 94.97 nanometers at the top. Well, look at the scale below. We go 0 all the way to 3,000 nanometers, and it's a linear scale. So the first tick mark on the bottom is at 500 nanometers. So if we looked at that, where would we put 94.97 nanometers? And the answer is right where that little tick is above the bar. So you can see that the first wavelength is already written there, and we'll be writing, let's see, 1, 2, 3, 4, 5, 6 more, or 5 more wavelengths on there, okay? And then for the energy level diagram, if you take a look here, we have n equal 1. Where did that bar come from? Well, for that, we have to go all the way back up here to the quantum number, radius, and energy. So do you see that energy of minus 2.1788 times 10 to the minus 18 joules? We'll say minus 2.2 times 10 to the minus 18 joules. Well, that is the energy written right there at this bar. If you take a look at the scale, that is minus 2.178 times 10 to the minus 18 joules. So that's for the first orbit. We're going to be drawing into that diagram the energy of the second orbit, the third orbit, the fourth orbit, the fifth, the sixth, and the seventh. And then finally, what we're going to do is we're going to try to identify, so this is a part 4, we're going to identify the following observed transitions. So how are we going to know what the transition is? And the answer is really simple. Do you see the wavelengths here? Based on Roy G. Biv, we should be able to predict what wavelength matches with red, what wavelength matches with blue, and what wavelength matches with violet. That should really be indigo, and then the other violet. And so what we do is we would look up these wavelengths here, and we look at, well, which ones are visible light? Okay, and then once we identify the visible light ones, we're going to say, well, which one of those is red? And then we could identify the transition, which is here, the M to N part. Okay, so Here, you'll notice we have these pre-laboratory questions, and some of these questions are going to end up in your assignment. And let's talk now. So your assignment, I'm going to want to see calculations. Well, actually, let's take a look here at what I want to write down. I'm going to switch my share screen right now. I'm going to do a new share, and we're going to go back and do some of these things right now before I get into the lab assignment. So now you should be able to see the desktop, and we have some very important equations written down here. So here's the speed of light is equal to lambda nu. Here is that the energy is equal to h nu. And if you combine both of these together, you get that the energy is hc over lambda. And this is Planck's constant here. You got Rydberg's equation, which is not worth memorizing. This is lambda. 1 over lambda is r, 1 over m squared minus 1 over n squared. Don't worry too much about these. And the Rydberg constant is 1.097 times 10 to the 7th inverse meters. I like to write it this way, 1.097 times 10 to the 7 over meter per meter. We have this equation where r sub n is 5.29 times 10 to the minus 11 meters times n squared. And we have E sub n is minus 2.18 times 10 to the minus 18 joules over n squared. Now, let's take a look at calculating the first 7 radii. So this is kind of a drawing of the chart we want. So for the quantum numbers or the orbits, we have the first, second, third, fourth, fifth, sixth, and seventh. And if we were to actually draw this, it would look kind of like this. If this were the nucleus, this would be the first orbit, this would be the second orbit, and this would be the third orbit, and so forth and so on. Now, I didn't try to purposefully make these orbits equal distance apart because we don't know if that's the case. That's something we'll figure out when we get the radius. Now we want all of our radii to be times 10 to the minus 2 nanometers. So let me show you how to get all the radii times 10 to the minus 2 nanometers. So what I'm going to do here is I'm going to show you how to calculate the radii. So this is the equation that we have from previously about the radii. And that is that the radius r sub n is equal to 5.29 times 10 to the minus 11 meters, and all of this times n squared. So we're going to change this around a little bit. Remember, when you multiply things, a times b times c is the same as a times c times b. So it doesn't matter how you arrange things. So I'm going to change this a little bit to 5.29 times 10 to the minus 9 times 10 to the minus 2 times meters times n squared. So I'm just going to get rid of that parentheses. And notice I made 10 to the minus 11, 10 to the minus 9 times 10 to the minus 2, because 10 to the minus 9 times 10 to the minus 2 is equal to 10 to the minus 11. Now I'm going to rearrange things a little bit. I'm going to put 5.29 times 10 to the minus, times, I'm going to cross that out. I'm going to put 5.29, and then I'm going to write n squared, and then I'm going to write times 10 to the minus 2, and then times 10 to the minus 9 meters. So you can see, here's my 5.29. My 10 to the minus 9 is now over here. My 10 to the minus 2 is now over here. My meter is over here, and my n squared is over here. I just kind of switched things around a bit. So now I'm going to do this, and this is the tricky part. I'm going to put 5.29 n squared times 10 to the minus 2, and 10 to the minus 9 is actually a nanometer, or a nano. So I can take this and switch it right to nanometer. So now I'm going to write 5.29 n squared parentheses times 10 to the minus 2 nanometers. So this is really convenient if I want to calculate the radii for the different orbits, and I want to get them all to be times 10 to the minus 2 nanometers. So you can tell if n is equal to 1, I've got 5.29. That's easy. What if n is 2? Well, 2 times 2 is 4. 4 times 5.29 is, let me see, 4 times 5.29 is 21.2 times 10 to the minus 2 nanometers. And you can do this all the way through 7, and it goes very quickly if you use this formula here and just plug in different n's and focus on this being in parentheses here, being this part right here. Okay? Now, what about the energy of the nth level? We can do the same thing. So here, down in this box, I'm going to put the energy of the nth level. Now we want all of these to be times 10 to the minus 18 joules. And we want this part here to be decimal form. We don't want it to be in scientific notation or anything like that. So what we're given for the energy is minus 2.18 times 10 to the minus 18 joules over n squared. So how do we get our answers to be all times 10 to the minus 18 joules? Well, we just make this equal to minus 2.18 over n squared times 10 to the minus 18 joules. And I'm going to put this in parentheses. And here, if we just focus on what's in parentheses, that's what's right here. So here, if n is equal to 1, what's the answer? Negative 2.18. What if n is equal to 2? What's the answer? Well, we do negative 2.18, and we divide by n squared. So if n is 2, we divide by 4. And we put the answer in, and the answer here would be 0.545 times 10 to the minus 18 joules. Okay, so you can see it's going to be really easy to fill out that table where you have the radii and the energy of the first 7 orbits. Okay? All right. So another thing we have to do, if we look at the parts, so let's go look at the directions here for the calculations. We calculate the first 7 radii, we calculate the first 7 energies, and then we calculate changes of energy and lambdas. So let's take a look at that. Calculating the change in energy and associated wavelength. Okay, so the one that they have for the different labels we're going to do, we're going to be doing label A, E, F, G, H, and I. And if I go back to that document and see which ones those are, label A is going from the 5th level to the 1st level. E is going from the 6th to the 2nd. F is going from the 5th to the 2nd. G is going from the 4th to the 2nd, and then the 3rd to the 2nd. And then we have for I, the 7th to the 3rd. Okay, so these are the change in energies we want to calculate, and these are the wavelengths that we want to calculate. So what I want to do is I want to show you how to calculate the change in energy, and I want to show you how to calculate the wavelength for this letter A, because we can compare it to what they have written in the document and see if we are right. Okay, so the change in energy is equal to minus RHC over n squared, which is negative 2.18 times 10 to the minus 18 joules over n squared. So R, H, and C are all constants, and when you plug the numbers in, you get 2.18 times 10 to the minus 18 joules, and then over n squared. And actually, I need to get rid of this. That's just the energy. So the change of energy is going to be the energy of the final level minus the energy of the initial level. Now, I don't like writing final and initial out, so I'm going to change that to the change in energy is equal to the energy final minus the energy initial. Now, what is the energy of the final level? It's minus 2.18 times 10 to the minus 18 joules over the orbit of the final level squared minus negative 2.18 times 10 to the minus 18 joules over the orbit of the initial level squared. We can clean this up a whole lot and make it minus 2.18 times 10 to the minus 18 joules times 1 over n final squared minus 1 over n initial squared. So if we wanted to do this calculation for 5 to 1, it would be minus 2.18 times 10 to the minus 18 joules times 1 over 1 squared. The final orbit is the first, and then minus 1 over n initial squared, which would be 5. So this is where a lot of people make the mistake of putting the wrong thing in the wrong place. Final is where you end up, and initial is where you start. So if we do this calculation, let's see what we get. So I'm first going to do 1 over 1 squared minus 1 over 5 squared. So basically that's 1 minus 1 divided by 25. And I get minus 2.18 times 10 to the minus 18 joules times 0.96. Now that seems about right, right? 1 minus 1/25 is 0.96. Okay, now I'm going to multiply that times this. Now these numbers, by the way, are exact. Orbits are exact. So these have infinite significant figures. So I'm going to multiply this number times that, negative 2.18 second EE negative 18, and I get 2.09 negative times 10 to the minus 18 joules. Now, this number here that I just calculated compared to what they have in the document are the same. The document has 2.0916. I've got 2.09, and they're both times 10 to the minus 18. Another difference, though, is that my answer is negative and their answer is positive. Which one is right? And the answer is, my answer is right. Because when an electron goes from the 5th level to the 1st level, and here's the nucleus, when the electron drops from the 5th level to the 1st level, what's happening is energy emitted. And that means it's exothermic, which means it should be negative. So contrary to what the document has, these answers should be negative. Not because it's negative energy, but because it's energy being released. Okay, so that's how you calculate the change in energy. Let me show you how to calculate the wavelength. Well, if the energy is hc over lambda, then the wavelength is hc over the energy. And you can put a change in energy there actually to calculate it. So let's calculate the wavelength. We have 6.626 times 10 to the minus 34 joule seconds. And I better make sure that you can see all of this. And it looks like you can. And we have 2.998 times 10 to the 8th meters per second. And then our change in energy was 2.09 times 10 to the minus 18 joules. Now notice here I didn't put the negative. I didn't put the negative because when we're calculating wavelength, there is no such thing as negative wavelength, just like there is really no such thing as negative energy. So here, why is this negative? It's because it's energy being released, but it's energy. So here I'm going to use the absolute value of the energy. And let's see what we get for the wavelength. I got 6.626 second EE negative 34 times 2.998 second EE8, and then divided by 2.09 second EE negative 18. Okay, and so what I get here is 9.50 times 10 to the minus 8, and joules cancel, seconds cancel, so that's meters. Now, I don't want this in meters. I want it in nanometers. So what I'm going to do is I'm going to take this 9.50 times 10 to the minus 8 meters. I'm going to multiply by 1 nanometer over 1 times 10 to the minus 9 meters. So basically, I'm going to take the number I got before and divide it by 10 to the minus 9. And I get 95.0 nanometers. And the answer that the handout gives is 94.97, which rounds to 95.0. So that's how you calculate the wavelength. So I've just shown you now how to calculate the wave energy, and I've shown you how to calculate the wavelength. Now, for the emission line spectrum, here, you're going to take these wavelengths and you're going to make the emission line spectrum. For the energy level diagram, you're going to take these energies and you're going to construct the energy level diagram. And then for the radius diagram, you're going to take these and construct the radius diagram. So that's what you're going to be doing in your lab. And then the last thing you need to do is part 4, where you have to take a look at these different wavelengths here and identify which ones are the colored ones. And you're going to do it based on the size of the wavelength. And then there you go. So the last little bit is, well, what is your assignment going to be? So let me write out for you what your assignment is going to be so you know precisely what to do. Okay, so your lab assignment. You know that the lab notebook is to turn in the introduction. It should not be as long as the introduction in the handout. It should be more simplified. You're going to put the safety issues, which of course are none because you're watching this on video and you're not doing it in person. But you might want to put down, if we were doing this in person, we'd want to wear safety goggles to protect your eyes from ultraviolet light. Then you're going to put the procedure, and the procedure is basically to calculate the radius, calculate the energy, calculate the change energy, calculate the associated wavelength. That's basically the procedure. And then you're going to show calculations. Now, for your calculations in your lab notebook, you don't need to show every calculation you've done. When you calculate a radius and you do it once, we assume you're going to do the rest the same way. So do one radius calculation that you put in your lab notebook. The rest you do on scrap paper and just put the answer down. For the energy of the nth level, there's only one that you need to do. The rest you do on a piece of scratch paper and put it into your table. So for all of those calculations, even though you're doing multiple calculations, you only show one example of each type and put it into your lab notebook. And you put the result in the table. Okay, for the lab assignment, what I would like to see is I'd like to see the table where you have the orbit. So that's the quantum number, the radius times 10 to the minus 2 nanometers, if I remember right. I'd like to see the energy, which is going to be times 10 to the minus 18 joules. And I'd like to see this for 1, 2, 3, 4, 5, 6, 7. I'd like to see that. I'd like to see the table for those transitions of A, E, F, G, H, and I, where you calculate the change in wavelength and you calculate the wavelength. I said change in wavelength. I'm sorry. I didn't say the right thing. It should have been change in energy. I'd like to see these two tables. I'd like to see the emission spectrum. So you should have, since there are 6 lines here, you should have 6 lines here. I would like to see the radius diagram and the energy diagram. So what's neat about these things is these should all be in your lab notebook. So you've already done that work. Great. Let's see what else you should be doing for your lab assignment. Okay, so what I'm going to do is I'm going to switch back to the assignment, to the Word document, actually, that has the assignment in it. And let's be clear about what we want you to do. So I'm going to do a new share, and we're sharing this document here, atomic spectroscopy. So in addition to those things that I just asked for, I would like to see the following things for your assignment. So look at number 4 and number 5. So here, rather than have you look at number 4 here, I'm going to write it out for you. Are orbits closer together for large n or for small n? So what you're going to be doing here is you're going to be looking at, say, 6 and 7, because those are large n's, and you're going to be looking at 1 and 2, and you're going to look at your radius diagram and see if they're closer together for 1 and 2 or 6 and 7. And then are the energies of orbits closer together for large n or small n? And here you're going to be looking at the energy diagram. Now, I'm going to be honest here. I don't know why, but a lot of students, when they answer these questions, they don't answer them the way I've asked them. So let's take a look at the questions as I've written them so that you can see them. So these are 2 questions that are part of your assignment. Are orbits closer together for large n or for small n? So we're looking at the radius. And then are energies of orbits closer together for large n or small n? And here you're looking at the energy. So what I hate is when someone answers the orbits are farther apart. Well, I didn't ask you where they're farther apart. I asked you where they're closer. So answer what's asked. Which ones are closer, large n or small n? Which ones are closer, large n or small n? So that's one of the questions you're going to answer. Let's see what else I would like you to answer, in addition to those tables I asked you about. Okay, so here we're looking at, I want you to answer 1 through 4 of the post-lab questions. Okay, 1 through 4 of the post-lab questions. So let's see what those look like. So I'm going to do a new share. So you can see question number 5 I wrote in by hand, but question number 1 is the ionization energy of the hydrogen atom is the energy required to remove its electron. Calculate the ionization of hydrogen with the electron in the first orbit. So for number 1, if we take a look at that, here's your nucleus, here's your n equal 1 orbit. Where does the electron end up? We're going to call that infinity. So the change in energy is going to be going from the energy of the final orbit, infinity, minus the energy of the first orbit, which is 1. And this, we have an equation, minus 2.18 times 10 to the minus 18 joules, 1 over n final squared minus 1 over n initial squared. And so this is the equation we're going to be using. You can't see it because I got to go back and change my share. So I'm going to change my share now. So while I was talking there and you were looking at that question, this is what we're looking at for question number 1, is if you're in the first orbit and we remove the electron completely, we would say that the nth orbit that we put it into is the infinitieth orbit, because that means it's not associated with the nucleus anymore. It's gone. So here, the change in energy is the energy of the infinitieth orbit, the final, minus the energy of the initial, the first orbit. So you would do this, and 1 over nf squared, 1 over ni squared. Ni is 1, and nf is infinity. I'll let you think about what 1 over infinity squared is. So that's what you would do for number 1 when you're calculating the amount of energy needed to remove an electron from the first orbit. So I'm going to go back to my share of the screen so that we can see the questions. So for number 1, you do this with the first orbit and you do this for the second orbit. You're calculating the energy it takes to remove the electron. Now, that should be an endothermic process because you're pulling a negative electron away from a positive nucleus. You have to put energy in. You should end up with a positive value. Okay, and then number 2, the electronic transitions resulting with an electron in the fourth orbit make up the bracket series of lines in the emission spectrum. Now, this is emission, which means energy is being emitted. Here, this is absorbed. Well, you can't see it, so I got to change my share. I wish there was an easier way to change share. So here, if we take a look at this, this is energy absorbed. If we had the opposite, this would be released. So this is exothermic and this is endothermic. So when we say released, we also say emitted. So for this question where they talk about the bracket series of lines being emission, you have to start high and go low. So let's go back to that question. So for number 2, when they say you end up in the fourth orbit, you have to start somewhere higher. So what's higher than 4? 5, 6, 7. Okay, examine the wavelengths of the 12 transitions. So we only did 6. You have to identify it and say whether it's ultraviolet, visible, or infrared. Those are the ones that I gave you. And then finally, you want to answer number 4. And actually, we're going to say 1 through 3 of the post-lab questions, and I'm going to tell you why. It turns out that question number 4 is part of your homework assignment. Okay, so that's going to be your lab assignment. I'm going to go back to my my other share so you can see what the lab assignment is. So the lab assignment, I'm going to circle that, is going to be these things right here, plus the tables I asked for. Okay, and so half of your lab assignment is a duplicate of what you've already done in your lab notebook, so that'll make your life a lot easier. And then you have to answer these 1, 2, 3, 4, 5 questions. All right, thank you for listening.